Hello, everyone. I am so sorry to tell you the second half of the recording of our previous session was not successful due to some technical issues. So here I'm going to re-record this part again. So let's start. So we are going to talk about the organic reactions, but since there are many organic reactions, pretty complicated with different mechanisms. So here we'll only pick up the most fundamental and the most important reactions. We'll start from the common function groups. So the idea is the same. There are so many different function groups, or we'll pick up a few. Okay. So the way I'm going to introduce the function groups are based on their oxidation level. So the oxidation level is determined by the central carbon, how many number of hetero atoms are connected to the central carbon. For example, alkane, we know alkanes are made by CC single bonds and CH single bonds. So both of these two types of bonds are relatively nonpolar. CH bond, although it's not completely nonpolar, but the electron activity of these two elements are pretty much the same. So we can say the oxidation number of the carbon in the alkanes is 0. So this is why alkanes are classified into the level 0 functional group. And next, we go to the alcohol and the ether, because the carbon, the central carbon, is connected to the oxygen, which is more electronegative than the carbon, and through a single bond. So this is why the carbon is +1. Supposing all of the other atoms connect to this carbon are either carbon or hydrogen, which means the oxidation number here is +1. So similarly, if the carbon is connected to a nitrogen or a halogen atom or a sulfur, all of them are +1 because all of those atoms are more electronegative than the carbon, which will make the carbon partially positive. And since they are all single bonded to the carbon, so this is why carbon is +1. So we can introduce the name of each type of organic compounds with those function groups. If there is an OH group, it's called alcohol. And if the oxygen is connected to carbons by single bonds, it's called ether. So you can see alcohol and ether are kind of quite similar, right? Because they both have an oxygen with 2 single bonds. But the alcohol must have a hydrogen connected to the oxygen. So this is the fundamental structure of the alcohol. And if the carbon is connected to a nitrogen, no matter what are the other atoms, the other 2 atoms can either be hydrogen or another R group, a alkyl group, or both hydrogen or both alkyl group. It doesn't matter. So all of them share the same stuff. The nitrogen has 3 bonds with a lone pair, or we call all of those organic compounds into amine. We can also call it amine. Later, we are going to talk about amines are weak bases, which is quite similar to the ammonia, right? And alkyl halides, I don't think we need to talk too much. We have fluorides, chlorides, bromides, and iodide. And the last one here is a thiol group, an SH group. SH is similar to the OH since the sulfur element is just below the oxygen in the same group. So the SH has pretty similar chemistry properties with the alcohol. The only difference is the acidity of these 2 groups. So similar to H2S is a stronger acid than water. We know water is neutral, and H2S is a diprotic weak acid. So similarly, the thiol group is slightly more acidic than the alcohol. Or actually, I should say much, more acidic than the alcohol if we compare the pKa values. So all of those are level 1. And then if the carbon is double bonded to a heteroatom, such as oxygen, nitrogen, or other elements, there will be level 2. So the typical examples are aldehyde, ketone, because the carbon is double bonded to the oxygen. Ketone is also the same. So let's move it here. Aldehyde, ketone. So I think we should make a comparison in between the aldehyde and the ketone. They are pretty similar. The major difference is the hydrogen here. If there is a hydrogen directly connected to the double bonded carbon, it is called aldehyde. And if there's no hydrogen, let's say there is an alkyl group, it's called ketone. So the difference in the chemical property of these two types of compounds are also highly related to this hydrogen, which will be introduced later. I think we can also, write down something like this, although it's not so important. The CN double bond. This is called imine, which is not listed here. So I think you can have a look. This is also level 2 functional group, right? And lastly, we are going to talk about the level 3, which means the carbon is bonded to 3 heteroatoms, or there are 3 bonds, connecting the carbon with the other heteroatoms, such as ester, carboxylic acid, and amide. So as you can see, let's start from carboxylic acid, a double bond and a single bond, right? So this is why it's level 3. And another one is the ester. Ester is quite similar to the carboxylic acid in structure, in terms of structure, right? Because we only need to, change the H into a alkyl group. And actually, ester can be produced by using, acid reacting with alcohol, which will be, introduced later as well. The last one here is called amide. So amide, obviously, is related to both acid and amine, if you can recall the amine. So the kind of, is the acid losing a OH group, and the amine lose a H group, and then they connect together and get the amide. So here the carbon is also +3, right? Is there any level 4 carbon? Yes, we do have carbon dioxide, although typically it's not regarded as an organic compound, right? And carbon dioxide, carbonic acid, carbonate, bicarbonate, right? So all of those are kind of +4 carbon. So moving from the left side to the right side, from level 0 to level 4, this process is called oxidation in organic chemistry. So I think it makes sense based on our definition of oxidation. The oxidation number should increase, right? So this is kind of an oxidation chain from the alkane to alcohol, and further to aldehyde, and then to carboxylic acid, and finally to carbon dioxide or carbonic acid. Yeah, so we answered this question. So this is a very brief introduction of different functional groups based on their oxidation level. Next, before we introduce the specific organic reactions, we want to have a look at the types of organic reactions. So we listed 4 different examples here. The first one actually is not a very typical organic reaction because this is just an acid-base neutralization, right? Such as the thiol group is slightly acidic. It can be neutralized by a strong base to produce the conjugate base and the conjugate acid. So we have a few typical function groups with this kind of acid-base property, such as the thiol group, the carboxylic acid group, the amine group. The amine has different type. Right? All of those are called amine because they all have the lone pair on the nitrogen. So let's take the first one as an example. So if acid is added, it will produce something quite similar to ammonia, right? Ammonia. So this is how the amine acts like organic base. I think this is the only basic organic compounds, the amines. There's one more group you can pay attention, which is also slightly acidic, is the phenol. Phenol, although it also have the OH group, OH as the function group, but this OH must be directly connected to a benzene ring or an aromatic system. If this is the case, we call it phenol, which is different from the property of the alcohol because this one is much more acidic. The pKa is around 10. So you guys can, think about why phenol is much more acidic than alcohol. We don't have time to, discuss this problem today, but I think we'll have some time to discuss it, in season 3. So no worry. So except the acid-base neutralization, we also have substitution, addition, and elimination. The reaction pattern of substitution is like this. Rx react with Y and change into Ry and X. So basically, it's the X group is replaced by the Y group. So this is quite similar to the double displacement in organic chemistry. And this is also why it's called substitution. I think it's pretty straightforward to understand the pattern. So here, there's an example. As you can see, the alkyl bromide reacting with sodium cyanate change into a nitrile with a CN bond. The organic compound called nitrile. And the Br minus is displaced and then bind with the spectator, the Na+. So this is quite similar to a double displacement reaction. But since we care more about the organic part, so we can say the Br is replaced by a Cn substitution. The next one is addition. Basically, we need to have a unsaturated bond, such a CC double bond or a CC triple bond or even a CO-CN double bond. So if we have an XY added, the double bond, one of the bond is gone, and X and Y is added to each side. So this process is a typical addition reaction. This is kind of somehow similar to the synthesis, reaction in organic chem. Let's have a look at this example. CC double bond reacting with HBr. The H is added, the Br is added. But you probably, realize there is some regional chemistry issue. So which place? Region. E, how to spell region? Region. I hope my spelling is correct. There's some regional chemistry. Basically, is which side add the H, which side add the Br. this is something we are going to discuss later. The last type of organic reaction is called elimination. Elimination is kind of the reverse reaction of the addition. So with some reagent help, the XY is gone, and then a unsaturated bond is produced. So the example is here. So as you can see, we add a strong base, and then the Br, and this H is off, changed into HBr, and the HBr reacting with the strong base to have a further acid-base neutralization, producing the conjugate acid and the conjugate base. And then the major part, organic compound, has a double bond. So this is called elimination. So with these three types of fundamental organic reactions in mind, we can further talk about a few typical examples of organic reactions. The first one is acid-base reactions. So such as the carboxylic acid reacting with the amines. So this is the proton transfer process. The acid will donate a proton to the amine and producing, the ammonia similar stuff, and also the acetate or the carboxylate. Okay? So we get a salt. anion is here, a cation is here. So this is why the amino acid, what is the amino acid? It's kind of, you have a amine group, at the same time, you have a COOH group. So when the amino acid is dissolved in water, there will be a intramolecular acid-base neutralization. Basically, is this H will be neutralized by the lone pair here. So change into COO minus, okay? So the major form of the amino acid in water will be something like this. This is called sweet ion. What is the meaning of sweet ion? Basically means in the same structure, one part is positive, another part is negative. So this is different from sodium chloride. If you put sodium chloride in water, it changes into cation and anion, they are separated. But here it's in the same molecule, one side positive, another side is negative. And it's not partially positive and partially negative. This is the real positive charge and the real negative charge. So this is called sweet ion. Yeah, I think we already, list the typical acidic and the basic functional groups in 2.2.1, right? So you can, review this part here, right? So let's continue. The next reaction is the esterification and saponification. We talk about esters, right? Esters has a structure like this. All of them have a COO group in the middle. So basically, they are made by an acid and an alcohol through dehydration, means they lose a water molecule. So if we cut the bond from here, the left part is the acid, the right part is the alcohol. If we cut from here, acid, alcohol, here, acid, alcohol. And actually, this is how you name the esters. Typically, you start from the alcohol's name and then ends with the acid's name. But we need to change the prefix and the suffix. For the alcohol, we change the suffix into YL, drop the NaOL. For example, here, ethanol change into acetyl, propanol change into propyl, and methanol change into methyl, and here the same propyl. And the acid change from the something oic acid, such as propanoic acid, 3 carbons, into OATE because it's kind of, the conjugate base, right? The anion. So it's called propanoate. And here it's methanoic acid. So it turned into methanoate. Here is butanoic acid turned into butanoate. Here is the same. Ethanoic acid turned into ethanoate. But you probably see the common used nickname for the methanoate as formic acid, formate, because the HCOOH, which is the methanoic acid, is common called formic acid. The name is related to ants because when you are bitten by the ants, you feel itchy. That because the ants kind of inject some formic acid into your skin. So this is why the HCOOH is called formic acid. Similarly, ethanoate is commonly called acetate because the CH3COOH is commonly called acetic acid. So obviously, both the acidic and formic are not the systematic name, but they are more commonly used. So I think you figure out how to name the esters, right? Starting from the alcohol part and then the acid part, but you need to slightly twist the suffix and the prefix. And then we are going to talk about the reaction of the esterification. So the esterification is the formation of an ester. It's reacted by an alcohol, ROH, with a carboxylic acid, a RCOOH. These two are not necessarily the same. And the reaction is catalyzed by a strong acid. And at the same time, this reaction is reversible. So I think it's good for us to add a reverse sign here, right? So let's have a look at how the dehydration process is ongoing. So the left part is the carboxylic acid, the right part is the alcohol. So you can see, from the dashed line, the carboxylic acid lose a OH and alcohol lose a H and then change into water. And then the acid part and the alcohol part bind together. But we can still see the acid fragment and the alcohol fragment, right? You can recall the nomenclature, how we name this process, right? So let's read the notes. The hydroxyl H of the alcohol combines with the OH or the hydroxyl group of the carboxylic acid to form water. And the hydroxyl oxygen of the alcohol, which is this oxygen, bonds to the carboxyl carbon, which is this carbon, to form ester. Makes sense, right? So the esterification, I think there is a typo, esterification is a dehydration process, which is a substitution, elimination, or addition. So I think this should be a sub reaction, right? A substitution. You can interpret in different ways. We can say the OH group in the acid is substituted by the RO group from the alcohol, right? So I think we can see, this is a substitution. Obviously, it's not an elimination because there's no unsaturated bond form. It's not addition because there's nothing added to a unsaturated bond, right? So there is a further question. How can we experimentally confirm the way of the dehydration process? Because we may also think about the dehydration process in this way. The acid loses the H and the alcohol loses the OH, right? We can also make the dehydration process. So in order to answer this question, we need to have a look at the mechanism. This is called the arrow push mechanism. So basically, the arrow means the movement of a lone pair. We're not going to discuss the arrow pushing based mechanism too much, but we try to get a sense what is the function of the catalyst of the acid, right? How does the catalyst, help the reaction to occur, right? Let's have a look. The first step, the H plus, is binded to the oxygen of the carbonyl group on the acid. And then this is kind of the acid-base neutralization, right? Acid-base reaction. The second step, as you can see, the double bond, CO double bond is gone and the ROH is added. This is kind of a addition, right? Addition, double bond is gone and the two atoms are added with different groups. The two atoms in the double bond, right? And the next step, what the next step here is the H plus from here is off. So this is also a acid-base reaction. And then this H plus is binded to a different place, to the OH group. So this is also a acid-base reaction. We call this into proton transfer. The proton is transferred from one place to another place. And then the key step is coming. This water is gone and a double bond is formed. A double bond is formed here. So obviously this is a elimination, right? Elimination. And the last step is this H is gone, is another acid-base reaction, right? So as you can see, the overall reaction is a substitution, but it is going through a few steps of acid-base neutralization or proton transfer, and a key step of addition and another key step of elimination. So what is the function of the acid here? I think in general, we can say the H plus is helping the dehydration process. Because the dehydration is from this OH. We need to change this OH into water. So this is why we need to have a H plus here to convert this OH into a water molecule. So the strong acid is to speed up dehydration. Dehydration. And if the alcohol oxygen is labeled as oxygen 18, which products will have the oxygen 18? So let's have a try. So let's say the alcohol, which is this oxygen, is labeled as, oxygen 18. So the 18 will be here. The 18 will be here. The 18 will be here. And finally, the 18 will be here. The 18 will be here. So it will be in the ester, right? Rather than in the water. If we go up back to our original discussion, if this oxygen, let me find a different color. Maybe use a green color. Maybe this one is good. If this oxygen is labeled as 18, since the dehydration process is from this OH and this H, so this oxygen will be kept in the ester. I think the color is not very strong. Maybe I can use the black stuff to emphasize it again. Yeah, but the idea is like this. So this is how we prove the mechanism, right? The dehydration is like this. And this method is called isotope labeling. Which is common, there's no double L, right? One L. So this method is commonly used to determine the mechanism. I think it's also used in biology to confirm, the mechanism of some process. The next question is how to increase the yield of the ester, since the reaction is reversible, right? If our goal is to get more ester, we may need to try to shift the equilibrium to the right side. So one common used way is to use concentrated sulfuric acid to catalyze the reaction, because this kind of reagent can absorb the water from the system, which is kind of decrease the amount of the water and shift the equilibrium to the right side. Another common used method is heating. The goal of the heating is to vaporize the water and make it leaving from the system and shifting the equilibrium. But if we need to do it in this way, we need to make sure the other reactants and the products will not be easily, vaporized. Otherwise, it doesn't work, right? Great. I think next we can have a look at the hydrolysis of the esters. There are two different mechanisms. The first one is the still acid catalyzed hydrolysis. As we discussed above, since the esterification is a reversible reaction catalyzed by acid, which means with the same acid, the ester can also react with water to hydrolyze, change back into the acid and the alcohol. Oh, it seems like there is one carbon missing here. It's called butyl. But we only see 3 carbons. So there should be one more carbon. So as you can see, we break the bond here. So this left part is the acid fragment, adding a OH from water. And the right part, the alcohol part, adding a H from the water. And then finally, they change back into acid and the alcohol. So this dashed line, clearly states, which place is the ester, break into two parts. So if we want to get more ester, we need to try to remove the water. But if we want to hydrolyze the ester, we add more water. Because this can help the equilibrium shift to the right side. But no matter what is the reaction, we need to have acid to catalyze it. Otherwise, if you just put the ester in water, it will not automatically hydrolyze because the rate is too slow. And also another reason is the ester is kind of non-polar, it's not that polar, so it's not very soluble in water. So there will be 2 layers, which means the ester will have very little chance to contact with the water molecules. So there are not so many collisions ongoing. Let's have a few practice examples about the products of the acid catalyzed hydrolysis of esters. An easy way is to cut the ester from here. So we can add a OH to the acid fragment, add a H to the alcohol fragment. So we got these 2 products. I think it's also a good opportunity for us to practice the nomenclature. So this one, we start from the alcohol part called acyl, and the acid part is benzoic acid. Benzoic acid. We need to change this into benzoate. Benzoate. So this is called acyl benzoate. The middle one, B, we also do something quite similar. We got propanoic acid and methanol. So this one, the ester is called methyl propanoate. The last one is a cycloester. This is called lactone. So the cycloester has a special name called lactone. So we still do something quite similar. So 1, 2, 3, 4, 5. There are 5 carbons in total. So we still add the OH to the acid fragment. We add the H to the alcohol fragment. So the lactone is made by the dehydration, a intramolecular dehydration. Intramolecular dehydration, which means in the same molecule, we have the COOH group and the OH group, and their distance is appropriate. And then with the catalyst, and they do a intramolecular dehydration and get the lactone. So obviously, it's relatively harder for us to name the lactone. Let's take a very small break, and then we'll continue the next part about the basic hydrolysis, which is also called the saponification. Oh, don't forget to subscribe my YouTube channel. When there's more videos coming, you will get notification. Thank you.